So let's consider an infinite swept wing, right? So basically I have a swept wing like that, and the flow is going here. Imagine the leading edge of the infinite swept wing. At the leading edge of the infinite swept wing, the flow, what direction is the shear stress? Right, or let me say, what is the UE at exactly the leading edge? What is the Q at the leading edge? It's not zero, right?
It's aligned with the sweep of the wing.
It's this direction, right? This is QE, is in this direction. Okay, so basically, if you consider exactly a 2D case with the same QE, you have a Blasius boundary layer, right? That's because the 3D swept wing is infinite and there is no difference between one point and another, so you won't expect the pressure to be either increasing or decreasing along the spanwise direction. So the pressure is constant. If you have no 3D effects, then under a constant pressure, with the velocity drifting towards that direction, towards like the lower part of the swept wing, you should have a Blasius boundary layer. But of course you don't. No end walls. It's infinite swept wing. It's actually exactly because it's infinite swept wing, there is no end walls. You shouldn't have a Blasius. Right. Do you expect the boundary layer to be thicker here, exactly at the leading edge, versus here? Just the two arbitrary points on the leading edge. So where is the boundary layer going to be thicker downstream or thinner downstream, or what it is?
Well, it will be developing as it moved.
Right,
So
right.
Thicken.
It should thicken, right? So how thick should it go? Should it become infinitely thick downstream? No, if you have an infinite geometry, it's translational symmetric, right? So I mean, so basically, an infinite wing means if you take the solution here and apply to here, it's the same, right? So whatever boundary condition, whatever boundary layer you have here is actually the same as the boundary layer here versus here versus here versus anywhere. So even though the velocity goes downstream, the boundary layer shape actually doesn't change. And why? Right, because it has very strong lateral dilatation at the leading edge. Right, so if you look at around the leading edge, what's the divergence of the two-dimensional velocity? It's very positive, right? So if you just go slightly above the leading edge, the velocity goes towards the upper surface. If you go slightly below the leading edge, the velocity goes towards the lower surface. So high divergence here of the streamlines. So if you look here, the streamlines are going like this, right? So and if you look underneath, it'll be the same. And if you look from leading edge or from the front of the wing looks like this, and exactly on the leading edge, the flow is towards the right, looking from leading edge like that. And slightly above it, the flow is going to go towards the upper surface. Slightly below it, the flow is going to go towards the lower surface. So if you look at here, there is a strong divergence of the flow here. And you can use the divergence theorem, because whatever flow goes into the here also comes out from the right. But on the top surface, all the streamlines goes out. On the lower surface, all the streamlines also goes out, right? So that means inside the leading edge, there is strong divergence of velocity. And the lateral dilatation effect actually makes the boundary layer thickens slower than usual.